Hello everybody, we are Group 8 and we will be presenting our project in this video. The aim of this project is to develop a method of analyzing photos of pets to determine its popularity, which is a tool for measuring how attractive pet photos will be. By determining the popularity, we can help animal shelters around the world to improve the appeal of their pet photos, generate interest and increase the rate of adoption of the animals. Submissions to the competition are scored based on the root mean squared error. One challenge of this project is that there are viewpoint variations in the images. This means that the object in the picture could be rotated and be of different sizes. The object could also be hidden behind other objects. To tackle this issue, we use data augmentation to generate images with different rotation, brightness, and zoom range to train the model with a variety of data. Another challenge is that it is difficult to identify and extract relevant features from the images and metadata, and some features may not be immediately obvious or easy to quantify. This means that careful consideration must be given to identify the most useful features. Different types of features may also require different extraction techniques. Thus, it is important to select the most appropriate feature extraction techniques. Integrating image and metadata in a classification model can be complex. For instance, the metadata might contain irrelevant features that could increase the complexity of the model and ultimately decrease its performance. In addition, determining which metadata features are the most important for the task and how they should be weighted relative to the image features can be quite challenging as well. Lastly, the model may not capture correlations between the image and the metadata features, which can lead to suboptimal performance. Overcoming these challenges requires careful feature selection and engineering to ensure the model performs optimally. The dataset used for this competition includes images of the pets as well as tabular data. The train set consists of 9,912 pet photos with hand-labeled metadata and a popularity score derived from page view statistics. The test dataset also consists of pet photos and metadata, similar to the train dataset. Pet photos of the test data have been augmented to look like the picture shown on the right.
Although we have explored various methods, we will focus on the methods which contribute to our proposed solution in this video. The first approach is EfficientNet. EfficientNet is a CNN which results in better performance by balancing various network hyperparameters, namely network width, depth, and resolution. As explained in the paper, a larger input image should require a deeper and wider network to capture more details from the image. Hence, the main idea proposed is to use compound scaling where the network width, depth, and resolution are scaled uniformly with fixed coefficient. This leads to higher accuracy compared to just scaling one dimension. The baseline EfficientNet B0 architecture is shown in this slide. The fundamental building block is the mobile inverted bottleneck convolution with squeeze and excitation optimization. The baseline model is scaled up using different values of the compound coefficient to get EfficientNet B1 to EfficientNet B7. In this project, we experimented using EfficientNet B0 to B2. We did not use larger variants of EfficientNet due to the limits in GPU memories. We conducted transfer learning with pre-trained EfficientNet models from Keras application trained on the ImageNet dataset. The pre-trained model were loaded and with the last layer removed and frozen. The model was trained using only images as input with data augmentation layers added and connected to the pre-trained model. A global average pooling layer, a dropout layer, and a dense layer were appended after the pre-trained model. The model was fine-tuned by unfreezing the pre-trained model and training end-to-end with a low learning rate. We also experimented using images and metadata as input. The images are passed into the EfficientNet model without the output layer, while the metadata is passed into a multi-layer perceptron. The outputs from both models are then concatenated and passed to a dense layer to get the prediction. The images were resized according to the specific EfficientNet variant used as shown in the table, as the pre-trained EfficientNet models from Keras application includes rescaling and normalization layer. We did not have to add them for pre-processing. For all EfficientNet experiments, 80% of the data from the train.csv file were used for training and 20% were used for validation. Using Keras tuners random search, we conducted hyperparameter tuning on the baseline EfficientNet B0 architecture to obtain the best dropout rate for the dropout layer and the best learning rate during training before fine-tuning. The ranges used are shown in the slide. Based on random search, the optimal hyperparameters after 10 trials are a dropout rate of 0.3 and a learning rate of 0.01. We utilize these hyperparameters for all our experiments. Different batch sizes were used for different EfficientNet variants as seen in this slide. For all experiments, we used Adam Optimizer and early sorting of 10 epochs based on validation loss. These are the results for training EfficientNets with images, and these are the results for training EfficientNet with images and metadata. To further improve on our public leaderboard score, we try weighted average assembles of the top 2 and top 3 and top 4 models from the previous EfficientNet experiment. The results are shown here. We can see that the weighted average assembled with the top 4 EfficientNet models gave the best public leaderboard score. The next approach that we'll be looking at is the swing transformer. The swing transformer is a hierarchical variant of the transformer architecture designed for natural language processing. It uses shifted windows to compute representation, dividing the input image into smaller windows processed by multiple transformer layers. This approach limits self-attention to non-overlapping local windows while enabling cross-window connection, leading to greater efficiency. The swing transformer has demonstrated superior performance on benchmark datasets such as COCO, ImageNet, and CIFAR, showcasing faster training time and better accuracy. It is a promising architecture for future computer vision research. The swing transformer architecture has several variants that differ in terms of the number of stages, layers, and patch used. We will be focusing on the swing B and swing L variants in this project. The swing B variant uses a base patch of 16 by 16 and is composed of 4 stages with a total of 32 transformer layers. The swing L variant, on the other hand, uses a large patch size of 32 by 32 and is composed of 4 stages with a total of 96 transformer layers. Images in the trained dataset were resized to 224 by 224 pixels, a requirement for the model use. Data augmentation techniques were applied during training to increase the dataset size, including brightness, contrast, hue, and saturation adjustment, enhancing the model robustness and generalization. We performed transfer learning on pre-trained SWAN B and SWAN L models with 22,000 images in the ImageNet dataset and fine-tuned on 1,000 images. The model used are shown on the second point. The model was fine-tuned using binary cross-entropy loss and a batch size of 32 for predicting popularity. K-fold cross-validation were used for fine-tuning on the Pathfinder dataset, with each fold used once for validation. The model was trained with a learning rate of 2e-5 and early callbacks to stop training, with the root mean square error deemed improved after 2 epochs. These are the results of a fine-tuned swing transformer model. To improve prediction accuracy, we utilized support vector regression with swing transformer. The swing transformer model extracted valuable features from Pathfinder data images, serving as input for the SVR model. K-fold cross-validation was utilized during the training of SVR models. For this purpose, we selected a swing large patch model that produced the best public leaderboard score in our previous experiment, trained with 5-fold cross-validation and 5 epochs. This is the result of our swing with SVR model.
Now, let's take a look at our proposed solution. From the EfficientNet weighted average ensembles, we observed that the ensembles resulted in better performance compared to their base models. Ensembles perform well, especially when the base models are independent. Hence, we experimented using a swing transformer and EfficientNet weighted average ensemble, since both models use different mechanisms to predict the outputs. For the swing transformer model, we tried 2 versions to combine with the best EfficientNet model, without SVR and with SVR. For the EfficientNet model, we used the best single model from the EfficientNet experiments, which is EfficientNet V2 using images and metadata. Various weightings were explored to create the best ensemble. These are the results. We can see that giving swing transformer without SVR a weight of 0.7 and EfficientNet a weight of 0.3 contributed to the best leaderboard score. Therefore, our proposed solution is the weighted average ensemble of swing transformer without SVR and EfficientNet V2 using images and metadata, where the weightings of the model is 0.7 and 0.3. Our proposed solution gives the best public score of 17.90253, which is within the top 25% of the public leaderboard. From this project, we learned that methods like dropout, L2 regularization, and early stopping are important to avoid overfitting the models on the training set. We also learned that transfer learning is useful as the pre-trained models, which have been trained on larger datasets, allow the models to learn better on downstream tasks such as this project. Finally, although weighted average ensembles are simple, the combination of predictions from different base models can contribute to higher performance compared to individual models. Thank you.